Polymers have the interesting feature that they have interesting properties that span a whole range of what we call time and length scales. In other words, there are things that I can change at the molecular scale of a polymer that will make a difference. There are things that I can change in the macroscopic scale by the way I process the plastic into a three-dimensional part. And so there are different types of models that can be used to understand these different scales. There are finite element models that can be used to understand the distributions of stresses and strains in a molded part. And there are molecular scale models that will allow us to say how will the molecules rearrange and on what time scale if heated or if a stress is applied to them in a certain way. And it's this latter category that is the focus of what we do in my research group, which is to develop the molecular models from the knowledge of the fundamental structure, the chemical structure, and also how the chemical structure is organized into morphologies within the material. By morphology, I can mean many of these plastics are what we call semi-crystalline, which means they're partially crystallized, partially amorphous materials. And the amorphous and the crystalline components contribute very different, make very different contributions to the final property of the material. In fact, I sometimes call semi-crystalline polymers nature's nanocomposite because it is a composite of a stiff, hard, crystalline lamellae, crystallite, embedded often within a more pliant, deformable amorphous matrix. And this is essentially a heterogeneous morphology that mimics many of the behaviors of what are called inorganic, organic nanocomposites. And so our molecular modeling tools allow us to anticipate what the properties are of the hard component, the pliant component, as well as the interfaces between them and how those two components will interact when subjected to a certain processing history or a certain load history. Semicrystalline morphology occurs naturally in nature, in plastics. It's a ubiquitous feature of semicrystalline polymers. The difficulty is we have very little ability to control in the ways we would like to be able to control the organization of that morphology. So the question can arise, how would I change the chemical structure of the molecule so that when it does crystallize, instead of forming this morphology, which is perhaps not as strong or not as permeable to a particular solvent or a gas, how could I restructure the molecule so that when it does crystallize naturally, it forms this alternate morphology that is somehow better suited to the application at hand? And so the semicrystalline morphology occurs naturally, but controlling it and making it do our bidding is a much more challenging task, and one that we're still trying to work on developing. Affinity, or likelihood to absorb, let's say, an organic material out of an aqueous solution. So now you have another way of separating oil and water by passing a current through the fiber, which is decorated with this redox active surface species, surface functional group. It will become oil-loving and absorb the oil species from the stream until it's fully loaded and reaches its capacity, and then you have to regenerate the material by passing a cleaning stream across it. Then you reverse the current, the surface functional groups expand, and they release the organics that they had absorbed in the previous cycle.